Hi, my name is Rishi Pathak, and this is my lab on constant velocity. I've titled it Observing and Modeling the Motion of a Golf Ball. So, a quick introduction of the premise of my lab. The purpose was essentially to investigate whether an untouched object with no non-negligible forces acting upon its direction of motion can move in a constant velocity. So, this question is actually quite important despite being seemingly trivial, as the results of it allow us to observe whether the Newtonian model of physics or the Aristotelian viewpoint of physics is actually correct. You see, if the ball's speed is constant, as in the ball continues to move without any net force acting upon it, then we would have proved Newton's first law, which states that an object that is moving will continue to move unless acted upon by an outside net force. Now, in order to test the hypothesis, I had to develop a model. In developing this model, I used three fundamental principles, excuse me. The first one is the idea of average velocity. So by definition, average velocity is equal to displacement divided by time. A bit of rearranging would give that equation as I've posited over on the slides. The second fundamental principle was the momentum principle, or Newton's second law, which states that a force gives rise to an acceleration, or a change in velocity, and that is directly proportional to the force applied. Or in other words, F equals ma. Now, finally, I also use the velocity update formula, which is the same thing as the definition of acceleration, or that acceleration is equal to delta v over delta t, with just a bit of rearrangement done. Now, a bit about the experimental setup. For the observation, I chose to use a standard golf ball and slide it upon a very, very slick wooden surface that was varnished to be very slick. Now, the golf ball is just a completely regular standard golf ball with the standard mass and diameter as stated in the slides. And I've also drawn a free body diagram and a coordinate system in order to better illustrate the forces that act upon the ball in order to develop a better model. So, as you can see, there are three forces that act upon this ball: the gravitational force, the normal force, and the frictional force. The normal force and the gravitational force can be said to be equal to each other because it's not like the golf ball accelerates in a positive or negative y direction. However, there is a frictional force, like a non-zero frictional force, because the ball does roll. However, since again, as I mentioned, it's slick. Since the wooden surface was very slippery, we can assume this frictional force to be very close to zero or almost negligible. Now, I've also drawn in the initial velocity, which I calculated uh, by finding the average velocity observed by finding the displacement in the between the first and two frames and dividing by the 0.008 seconds that elapsed between these frames. And since the ball was going to the left, the initial velocity ended up being negative 0.878 meters per second. So here's a picture, a little video of this ball. I've slowed it down a little bit since it was way too fast to see. Okay, so a little bit about the setup of the model. So as you can see, I set the initial conditions like mass, position, initial position, and then initial velocity at the very start of my code. And then for the loop, I set t to last to be less than or equal to 0.45 seconds, since that's how long the ball took to move from right to left of the table. Now, the initial force vector was set as zero, like the net force vector was set as zero, as all forces balanced out in our experimental study. However, the only way, it's also to be noted that the only way for the velocity to actually be constant is if the net acceleration was set to zero or the net force was set to zero. So that's also why I set the net force to zero. So then using the velocity update formula, I updated the ball's velocity at each iteration. However, note that since the acceleration was always zero, since the force was zero, the velocity was always constant. Finally, I calculated the position of the ball using the ending velocity across the time interval. In order to do this, I assumed average velocity is equal to final velocity. And I will discuss that more in just a sec. Finally, I outputted the value of the position as a graph over time. Okay, so a bit about the average velocity thing. So in order to better illustrate that bullet point, I've drawn out pictures of what's actually happening in each iteration. So since the net force is zero, and if we divide that by mass, we'll get a net acceleration of zero also. Then if we multiply the net acceleration by delta t to find the change in velocity, the velocity update formula, across the time interval to get the change in velocity. Now this is equivalent to taking the area under the acceleration curve, which is always zero in our case. Now, we add this change in velocity to our initial value of the velocity when the time interval just started to get the final velocity. In order to find the change in position, we actually would have to take the average velocity and multiply it by delta t, or the area underneath that curve. However, since as the picture shows, final velocity equals initial velocity and acceleration is zero, we can safely say that v average is equal to v final. Thus, we can find the change in position with velocity final times delta t. Now here's a picture of the model as it moves. A quick discussion of the results between the model and the experiment. So as you can see, the model and the experimental position followed each other very closely. So it was very accurate. However, there's a slight deviation as time increases, which suggests that there was a very slight error. This is likely because there's some amount of human error occurred that in recording the initial estimated velocity, maybe placing placing the center of the ball incorrectly. So therefore, we can theorize that the ball did move in a constant velocity without the influence of any force in the x direction. This, in fact, does prove Newton's first law.